So Apple released the M1 chip, and benchmarks from it seemed almost impossible. Tech enthusiasts are raving about it and praising Apple. In some cases, it outperforms desktop computers using just a fraction of power. So something must not be right? Why Intel or AMD are not able to create such a chip? Well, in some sense, this chip is like a chip from the future, like a lot of mobile chips actually in these days are. It is built on TSMC's 5nm process and custom ARM architecture. Intel is only now wrapping up 10nm production, which is comparable to TSMC's 7nm, and AMD will release their 5nm version sometime in late 2021. But that is not all. One number that could describe and illustrate the source of power for this chip could be its transistor count. 16 billion. Okay, so how much is that? Well, Intel 28-core server CPU based on 14nm and Skylake architecture has 8 billion transistors, half of M1's transistor count. So how is it possible that it uses less power? And the answer lies in the fact that simply less of these transistors are switching on and off. These ARM chips in some very specific ways are simpler. So the cost of them goes down if the production is at truly massive scale. There are simply less defects when they are produced, or these defects don't affect them so much because you would really feel them if the frequency would go up. But if the frequency stays low, then it's not a big deal. I also have to mention that pre-built computer manufacturers like Puget Systems were quick to dismiss that laptops powered with M1 could replace a powerful workstation desktop PC if the workload is complicated and M1 low optimization could not be leveraged. But of course, such chips and solutions are a direct threat to their business. So of course, it's understandable that they would like to show these solutions in the worst lighting possible. Because ARM is based on reduced instruction set architecture, it needs more instructions to do even simple tasks. But traditionally, such solutions do suffer from lack in the single-core performance department. But actually, there are some things that you could do in order to increase the single-core performance. For example, what happens when you design it with higher memory bandwidth and lower latency there? That obviously helps with sequential tasks. But the only thing is that such solution would be more expensive. And this packaging technology as such is more complicated. But Apple has no problem selling expensive devices as they are. And Apple chips overcome these limitations with having these regions on SoC. And these ARM chips and other RISC-based architectures have a different approach in getting high performance in these very specific computationally intense tasks. They have these regions on SoC which do a very specific task that is needed for a given device. So the user does not feel the lack of computational power in day-to-day usage. Where computers from CISC era boasted about how versatile they are, how you can mix and match components, and how economical they are in their memory usage. But memory is now cheap. It used to be that the RISC architectures were viewed as some kind of a regress from the computer scientists and electrical engineers who worked with the CISC architectures. But as now software optimization is one of the most important places where you can get the performance uplift, these more flexible RISC designs really show their power. In PCs, we can get comparable performance uplifts as these custom ARM solutions with PCIe expansion cards. For example, video encoders, decoders, GPUs, ASICs, FPGAs. But they go through cumbersome communication that needs to be compatible with many devices. And then they don't really share their own resources with other parts. But if you know what generally you will need to accelerate in this device that you are building, you can limit its flexibility and just by design create a lot more efficient and faster architecture and put these different computational devices very close to each other. And because portable devices like smartphones, tablets got so popular, there was a large investment into developing such SoC solutions. And even the leading semiconductor company has optimized their nodes for this purpose: low power usage and high transistor density, even if that means lower frequency. And it's not just the software stack and the technology that gets developed there, but also people who have the right training and understand the benefits of this architecture and how to work with it. Because, for example, every large company needs also, let's say, a iOS version of some app, and they really need to learn how to optimize things for their hardware. So M1 marks a new era for high-performance computing, where most of the magic happens in optimization in lower software levels for SoCs with diverse feature set. And I would like to take a moment to amaze how balanced this M1 chip is across the different computational types. There is the simple scalar computations, which we know as the source of power for sequential calculations, and other types of calculation can be done with these scalars. They are essentially simple Turing machines. Then there are vector or parallel processing devices like GPUs that essentially are many of these Turing machines put together in this lines kind of a shape. And finally, matrix multiplication devices like different AI accelerators. And you can imagine them as tables of Turing machines. Good examples of that would be RT cores in NVIDIA GPU, AVX512 instructions in CPU or Google TPU processors, or some other NPUs or whatever they are called now. And now you have all these areas covered in one chip, and the trick is to write software in a way to leverage what you have on this specific chip. And I think that one of the most powerful advantages Apple has with these M1 chips is that they are mostly the same for every tier of MacBooks, at least until the M1X is released. This gives developer the advantage of directly testing their software on one device and optimizing it for it. Of course, it is a lot harder to do if you have an old, hard to manage code base, like for example, Adobe has. Adobe already mentioned that they will need extra time to optimize their software for it. But imagine if you as a developer know that it is guaranteed that you will have 8 cores at your disposal, and this is a constant. Then you can write without any thinking a lot of algorithms and tasks and split them exactly in 8 parts, not check how many cores there are, how many threads, what are they doing, and things like that. You don't need to manage them directly. Maybe the operating system already knows which are the best cores and things like that, and you can simply assign the heaviest task to that core or something like that. And as now a lot of developers are really interested in integrating some AI functionality or replacing some heavy algorithms with AI models, you can specifically tailor these models to the AI capabilities of this chip. But for now, support of these technologies is limited. Even if you would like to run AI inference on an ARM chip, let's say if you're using a deep learning framework like TensorFlow, for example, you would need to use TensorFlow Lite to run it on ARM chip. And most of the development is very specific to CUDA and Google's TPU there. Maybe at the moment, hotter framework is Facebook's Torch or PyTorch, and it has ARM support. But for these technologies to get adopted, there is a need to have a push from Apple's side. They need to develop an easy to use technology stack, training, examples, and collaborate with developers of these frameworks to make adoption fast. Otherwise, all this potential will just sit on a shelf, like it is happening with AMD GPUs actually. They are still not officially supported by Torch, for example, and only somewhat supported by TensorFlow. I guess more in the latest versions of TensorFlow. But I think that the biggest advantage Apple has is their marketplace, where developers know that their apps will sell well if they will run well on Macs and iPads and other Apple devices with similar hardware. And if they will not adopt these technologies, they will fall simply behind. And as Apple owns impressive and powerful creativity software like Final Cut Pro and Logic, which must seamlessly integrate with acceleration possibilities of this neural engine and other things, other developers will need to push their integration as well to be competitive. So this is briefly my explanation why M1 is performing so well and what are the possibilities and future prospects of this technology. Hope you like it, and that's it.